Hello and welcome back to my YouTube channel. In this video, we'll be learning about a ParaView. A ParaView is an open source multi-platform data analysis and visualization software developed by Kitware. So here you see in the gallery that you see all these beautiful high resolution images, which is anyway impossible to draw and visualize in any other open source software. So today we'll be learning how do we use ParaView, how to download it, how to get the basics of ParaView, and how do we use it to integrate it into our finite element analysis codes so that we can solve it using any of the language like Python, MATLAB, or C++, or any open source libraries, but we can visualize the results in ParaView effectively. So just I'll download the documentation and show you how it looks like. So this is the normal interface of ParaView, and you get a lot of options, an array of options here. So here you'll get how do you visualize the animations, the static part, how much variables that you want to show one at a time, and how do you apply some calculations or some post processing to your data, how do you interact with the 3D view, and the animation part is really good. It takes very less time to simulate a multi time steps solutions. So now you can also apply different color maps to a variables, add vector glyphs. Also, you can save a screenshot. Right now, you cannot save an animation as it is, but maybe possibly in future you can have that option as well. But now you can have a static screenshot as of now. And to get additional help, you can get to all these contacts. So now we'll just go on with the installation part. It's a normal installation setup wizard. So you just click on all the acceptance of the license and then clicking on next. You get all this information. And in the meantime, while it's downloading and installing, I'll just brief you about my journey. So what usually happened, I developed a lot of codes in MATLAB. MATLAB is inherently slightly slower than the contemporaries Python and C++, but still the speed for solving is manageable. But when you want to visualize the data, when you want to show some meshes on which some two-dimensional or three-dimensional data are there, then it becomes a headache. Plotting on a fine mesh in MATLAB can take up to eternity. So with all the choices I had, I thought I bottled down to ParaView and thought this was the best possible option out there. And after trying, I can be very sure that this is the best open source software that you can get. So to visualize your data. So I'll just open ParaView now. It's been installed. So this is the basic interface. I'll just zoom out a bit. So now I have this FEM solution that I was solving for a phase field solver, and it is a scent specimen loaded in a uniaxial tension, and you can see the crack propagation here. So first you will get all these variables on the left hand side, and then you click apply. And this is, mind you, that this is a PVD file. For a video animation, you have to have a PVD file. For a static, we have to have a VTU file. So as you can see, you'll see that the crack starts to evolve once enough loading is applied. And this red line, this is the indicator of a phase field parameter phi, where the red means that the material is completely broken and it is synonymous to a crack. So here you can see that this visualization is taking very less time, although it is working on a grid of 12,000 elements and 15,000 nodes. So now you are trying to visualize the UI, that is the V. And this is the displacement control that we were applying. We were fixing the bottom end and stretching on the top end in the Y direction. And you can see that there is the steering happening at the interface. Similarly, you can imagine a lot more things. Here I have also calculating stresses. So you can visualize the stress. This is the sigma YY. This is the dominant stress that is going to drive this fracture problem. And you can see all these beautiful images that comes at various time intervals. You can just pause it somewhere and take a screenshot, or also you can just visualize the data from here. Again, if I want to visualize the shear stress, sigma xy is very small compared to the sigma xx and sigma yy in this case, because it's a plane strain problem and dominated primarily in the y direction. But still, you can see all these anti-symmetric stresses there that is synonymous to a single edge notch tension problem. So all these results, visualization, editing, post-processing can be very easily done in ParaView. So how do I write it? So I have created these functions which I'll be posting on my GitHub page. You can download it directly from there. So what it does, it creates an unstructured VTK file on which all the writings is done. So I have these three functions. First is the VTU time series mesh, simple VTU mesh, and the PVD sort. So this PVD file, what it does, it just takes on the stack of the VTU files and integrate it into an animation. The primary function is the write VTU mesh, where you have to give in your file name, your mesh parameter like the node and the connectivity info, and the point data and the cell data. Point data are the nodal fields and cell data are the elemental fields. So also you have to make sure that even if you are solving in 2D, you have to add the third row, because ParaView always takes 3 coordinate system as its input. Although it's a 2D file, but still it needs that. So you have to create this unstructured grid with all the nodes, connectivity info, and all the nodal parameters. And you can have as many variables as you want. There is no limit up to it. But mind you that increasing the number of variables increases the file size, and with a bigger file size, it will take more time to process. So all these point data and cell data are saved in a certain way, and this certain way is already very rigorously tested and provided in this code. So you can use this code as it is. You just need to have a node and a connectivity info and all your mesh related nodal variables and the elemental variables. So you can just put it here and write a very beautiful VTK and PVD file, which you can visualize very easily. So this is a sample code. This also I'll be sharing with you. So once after solving, I have some nodal and the elemental variables. So how do I store it in a way? So I just create a structure of point data and cell data and have different variables inside it. I save all those values from the results that I've already created. And then I just save it and allow my function to do the rest. My output is a PVD file and a series of VTU files. So you can experiment it a lot. And mind you, this is for a quadrilateral linear mesh. So if you have linear quads in 2D, this works fine. For other types of meshes, you have to be careful. You have to make certain changes, which you can find very easily on the internet, or you can ask ChatGPT for it for your help. So now all these point-wise, element-wise stresses, and these are all average stresses, and this is the function calling. And just to check whether all the point data and cell data are there, I just print those field names. So you see in the point data, you have ux, uy, and phi. And for the cell data, you have these eta components, h, and the stresses. Now going back. So what does this eta do? So eta is a error residue indicator. So what it actually does, it shows you a local graph, a contours of the places where the elements have the highest errors. So in a sense, this can guide you for adaptivity. So this is the project I am currently working on. So we are trying to visualize how the errors locally behave in phase field simulations. So now you can visualize this is the earlier was the error in the U or the strain energy. Now this is the error in gamma or the phase field variable. So you can see you have these different types of contours, and you see at the intersection of different types of meshes, you see a lot of issues there. And also at the boundaries, you see a lot of errors. So now you want to visualize the mesh. You can see the mesh is very, very fine where the crack path is expected to propagate. And this is the reason why my MATLAB solver was crashing a lot when I was trying to plot it in MATLAB. So then I had to figure out my alternatives, and ParaView came to rescue. I can see you can zoom in, zoom out very easily. It does not take at all any processing. And you can also visualize your variables on this mesh. So if I want to see on which elements or which edges this was evolving, but anyway, this is much clearer. If I take only surface, I can also go in the forward direction or in the backward direction, stop at any time, take a screenshot. Also, I can do this filter option. In filter, I have various options, but some of my favorites are like plotting over a line. So I'll just search it where it is. So it here. So plot over a line, what it does, you have this line and you can plot all the variables that vary along this line. So I'm just changing the location of the line. Click apply here. And you see all the variables that I had in this file now are plotted as a function of that line. So now if I want to change, I want to see only few of them. So I'll just click here and then select. So now you see only UX and UY. And as expected, you see a very linear behavior for UY and a simple sinusoidal for UX. Now, if I also want to add phi, you can see the profile of phi. Phi is actually the damage or the fracture indicator. So wherever the phi is larger, close to 1, we assume that the fracture is already happened there. Now, these are the stresses that I want to plot, and this is along this line. I can also change the location of this line, orientation of this line, and figure out whether my stresses that I'm getting locally are in accordance with the linear elastic fracture mechanics or some other theory that I want to validate. These are the error indicators, particularly in U. And you see, as you go to coarser meshes, from the fine strand, you get higher errors. And I'll just show you a PVD file in a notepad. So if I open this PVD file, you'll see that this is just containing the information that you have to open this VTU file when called upon. So this is the series of 100 VTU files, which this PVD file is reading one after the other. So if I just take one of the VTU files here, so you'll see that you cannot have an animation out of it. It's just a static thing. So it is just at the 100 time step. When the analysis was over, this was the final analysis, final step. So you see, even if you select the play button, it does not change. And you can visualize all the things for that particular time step, but you cannot change from one time step to another when you're opening a VTU file. In PVD file, you can do all of that. So at the last final time step, this is the variation of all the different variables that we have saved. So that's it for today. See you in the next video. Thank you.